An engineering drawing, a type of technical drawing, is used to fully and clearly define requirements for engineered items. Engineering drawing produces engineering drawings, more than merely the drawing of pictures. It is also a language, a graphical language that communicates ideas and information from one mind to another. Most especially, it communicates all needed information from the engineer who designed a part to the workers who will make it. Relationship to artistic drawing. Engineering drawing and artistic drawing are both types of drawing, and either may be called simply drawing when the context is implicit. Engineering drawing shares some traits with artistic drawing in that both create pictures. But whereas the purpose of artistic drawing is to convey emotion or artistic sensitivity in some way, the purpose of engineering drawing is to convey information. One of the corollaries that follows from this fact is that, whereas anyone can appreciate artistic drawing, engineering drawing requires some training to understand. But there is also a high degree of objective commonality in the interpretation. In fact, engineering drawing has evolved into a language that is more precise and unambiguous than natural languages. In this sense, it is closer to a programming language in its communication ability. Engineering drawing uses an extensive set of conventions to convey information very precisely, with very little ambiguity. Relationship to other technical drawing types. The process of producing engineering drawings, and the skill of producing those, is often referred to as technical drawing or drafting, although technical drawings are also required for disciplines that would not ordinarily be thought of as parts of engineering. Persons employed in the trade of producing engineering drawings were called draftsmen in the past. Although these terms are still in use, the non-gender specific terms draftsperson and drafter are now more common. Cascading of conventions by specialty. The various fields share many common conventions of drawing, while also having some field-specific conventions. For example, even within metalworking, there are some process-specific conventions to be learned. Casting, machining, fabricating, and assembly all have some special drawing conventions, and within fabrication there is further division, including welding, riveting, pipe fitting, and erecting. Each of these trades has some details that only specialists will have memorized. Legal instruments. An engineering drawing is a legal document, because it communicates all the needed information about what is wanted to the people who will expend resources turning the idea into a reality. It is thus a part of a contract. The purchase order and the drawing together, as well as any ancillary documents, constitute the contract. Thus, if the resulting product is wrong, the worker or manufacturer are protected from a liability as long as they have faithfully executed the instructions conveyed by the drawing. If those instructions were wrong, it is the fault of the engineer, because manufacturing and construction are typically very expensive processes. The question of liability for errors has great legal implications, as each party tries to blame the other and assign the wasted cost to the other's responsibility. This is the biggest reason why the conventions of engineering drawing have evolved over the decades toward a very precise, unambiguous state. Standardization and disambiguation. Engineering drawings specify requirements of a component or assembly which can be complicated. Standards provide rules for the specification and interpretation. In 2011, a new revision of ISO 8015 was published containing the invocation principle. This states that, once a portion of the ISO geometric product specification system is invoked in a mechanical engineering product documentation, the entire ISO GPS system is invoked. Quote, It also goes on to state that marking a drawing tolerancing ISO 8015 is optional. The implication of this is that any drawing using ISO symbols can only be interpreted to ISO GPS rules. The only way not to invoke the ISO GPS system is to invoke a national or other standard. Now in 2015, there is a new standardization called BS 8888. This is now used for all standard and technical drawings. Since there are only two widely standardized definitions of size, there is only one real alternative to ISO GPS i.e. ASME Y14.5 and Y14.5M. Standardization also aids internationalization, because people from different countries who speak different languages can read the same engineering drawing and interpret it the same way. To that end, drawings should be as free of notes and abbreviations as possible so that the meaning is conveyed graphically. Important note: the manufacturing of a technical drawing, however, is as difficult as the actual production of the design it describes. Therefore, engineers must think very clearly about what is placed on a drawing, i.e. dimensioning and tolerancing principles. Ideally, each party knows exactly how to read and interpret such principles, but practice shows it is not as easy. Media. For centuries, until the post-World War II era, all engineering drawing was done manually by using pencil and pen on paper or other substrate. Since the advent of computer-aided design, engineering drawing has been done more and more in the electronic medium with each passing decade. Today, most engineering drawing is done with CAD, but pencil and paper have not disappeared. Some of the tools of manual drafting include pencils, pens and their ink, straight edges, T-squares, French curves, triangles, rulers, protractors, dividers, compasses, scales, erasers, and tacks or push pins. And of course the tools also include drawing boards or tables. The English idiom, to go back to the drawing board, which is a figurative phrase meaning to rethink something altogether, was inspired by the literal act of discovering design errors during production and returning to a drawing board to revise the engineering drawing. Drafting machines are devices that aid manual drafting by combining drawing boards, straight edges, pantographs, and other tools into one integrated drawing environment. CAD provides the virtual equivalence. Producing drawings usually involves creating an original that is then reproduced, generating multiple copies to be distributed to the shop floor, vendors, company archives, and so on. The classic reproduction methods involved blue and white appearances, which is why engineering drawings were long called, and even today are still often called, blueprints or blue lines, even though those terms are anachronistic from a literal perspective. Since most copies of engineering drawings today are made by more modern methods that yield black multicolor lines on white paper, the more generic term print is now in common usage in the US to mean any paper copy of an engineering drawing. In the case of CAD drawings, the original is the CAD file, and the printouts of that file are the prints. Relationship to model-based definition. For centuries, engineering drawing was the sole method of transferring information from design into manufacture. In recent decades, another method has arisen, called model-based definition, a digital product definition. In MBD, the information captured by the CAD software app is fed automatically into a camera, and is translated via post-processor into other languages such as G-code, which is executed by a CNC machine tool. Thus, today it is often the case that the information travels from the mind of the designer into the manufactured component without having ever been codified by an engineering drawing. In MBD, the dataset, not a drawing, is the legal instrument. The term technical data package is now used to refer to the complete package of information that communicates information from design to production, spec revisions and addenda, and so on. However, even in the MBD era, where theoretically production could happen without any drawings or humans at all, it is still the case that drawings and humans are involved. It still takes CAD/CAM programmers, CNC setup workers, and CNC operators to do manufacturing, as well as other people such as quality assurance staff and logistics staff. These workers often use drawings in the course of the work that have been produced by rendering and plotting from the MBD dataset. When proper procedures are being followed, a clear chain of precedence is always documented, such that when a person looks at a drawing, he is told by a note thereon that this drawing is not the governing instrument. In these cases, the drawing is still a useful document, although legally it is classified as for reference only, meaning that if any controversies or discrepancies arise, it is the MBD data set, not the drawing, that governs. Systems of dimensioning and tolerancing. Almost all engineering drawings communicate not only geometry but also dimensions and tolerances for those characteristics. Several systems of dimensioning and tolerancing have evolved. The simplest dimensioning system just specifies distances between points. Since the advent of well-developed interchangeable manufacture, these distances have been accompanied by tolerances of the plus or minus or min and max limit types. Coordinate dimensioning involves defining all points, lines, planes, and profiles in terms of Cartesian coordinates, with a common origin. Coordinate dimensioning was the sole best option until the post-World War II era or the development of geometric dimensioning and tolerancing, which departs from the limitations of coordinate dimensioning to allow the most logical tolerancing of both geometry and dimensions.